We will start with lecture 15, in which we are going to look at binary to access 3. So in binary to access 3, the input is binary, output is access 3. So what we try to do is, as usual, with respect to the various other what we have seen is various code converters. In binary to access 3, what we try to do, first step, develop truth table, then write expressions for output, then get a simplified expressions for output in terms of input. Then from the expressions, we try to draw the circuit diagram, which is the final step. Now look at the input output relations. Now if you look at the input output relation, that is step 1, of course. So this is your step 1. In the step 1, we are looking at the truth table. Input is binary, output is access 3. Anything rather than 12 is don't care. That is what exactly we are considering, because the output valid output is from 3 to 12. Okay, because output is access 3. Input is binary. Of course, I can take binary from 00 to 1001. Rest are also valid, but there is no equivalent access 3 code for the binary code. That is the reason why. So we are not going beyond 9, because this is also not valid. Okay. So with respect to the output, this is exactly the case. Now what we try to do is, we try to see the expression, say A is a function of x comma y comma z comma t. Similarly B. Okay. Similarly C. Similarly D. So what we try to do is, in step 2, we try to write the expressions for A, B, C, D. Then if you look at A, it is 1 for which min terms? Say for these terms it is one, min terms 1. Min term, this is 5, 6, 7, then 8, 9. And for rest of the terms, so what is by default don't care. So the default don't cares are starting from what exactly is 10, 11, 12, 13. So by default, all don't care terms will be there for 10, 11, 12, 13, 14, and 15. Okay. So for example, for A, for the min terms, so A, for example, sigma m, what are the min terms that we have? Are say for example here it is for 5, 6, 7, 8, 9. So 5, 6, 7, 8, 9. Right. Similarly, we can write for B, C, and D. So in subsequent pages, slides, I can say, we can look at the input output comparison. Then directly we can enter into the map. So what is known to us is, don't guess, 10, 11. This is 10. This is 11. 12, 13, 14, 15. Next. For what it is 1? For 5 it is 1. This is for 5, 0, 1, 0, 1, 5, right? Next, 5, 6, 7, 5, 6, 7, 8, 9. So this is 8 and this is 10. So what I can do is, I can go for this combination. Okay. I can go for this 4 combination. I can go for this 4 combination. For each and every combination, I can write the expression. From this, what exactly this one? From this, if at all see, this is x. Plus, if you see expression for this, in this, what is common here? What is common here? This is common, y is same. So y. And what about here? T, y, t. What about this one expression? In this, what is common is z, and what is common is y. So yt and yz. So x plus yt plus yz. This is what exactly we have got it. Next, what I try to do is, we will go for the next term. So what I am looking for here? I am looking for B and C. So let's look for the expression B. What is known for us? These are dot k terms which we have come across. Now look at the terms for which it is 1. So for 1, 2, 3, 4 it is 1. 1, 2, 3, 4. So this is 1, 2, 3, then what exactly 4. is 1. Anything more? Then 9. So where is 9? 9 is here. This is 8, this is 9. So for 9 it is 1. So what I try to do is, I can do something like this. I can combine these two. I have no other option. I can combine these two with this two. Then I can combine these two. I can combine with this two. Okay, I can write the expression. So what is the expression for this? Let's say. So for this, what is common here is y bar. Y bar. What is common here is t. Y bar t. One of the expression. What is this expression? Z bar t bar. What is common here? Y. So y bar y z bar t bar. What about this one? This expression for this is y bar, and whereas here is z. So y bar z. So one is y bar z, another one is y bar t, then y z bar t bar. Next, what exactly that I am trying to look at is C. For C, what exactly that is happening is, once again same story. With respect to the don't cares, it is same. And with respect to the min, for which min terms it is 1? It is 1 for 0. Nice. Then 1 for 3. 1 for 3. Then 1 for 4. 1 for 4. Then 1 for 7. 7. 1 for 7. 1 for 8. 7 is here. 8 is here. Then 1, 7, 8. Totally 5 ones. Okay, done. So what I can do now is, I can combine these terms, right? So once I combine them, what I am going to get is, for this C, it is for 0, for 3 and 4, 7 and 8. 3, 4, 3, 4, 3 is missing. Okay. So here, if I look at, this is 2. 2 is not there. 2 is 0. So just erase this. Okay. So now if you look at here, okay. So what I am trying to do is, just go up. I can combine this 4. Let me take the pen. Combine this 4. Then you can combine this 4. So when I combine this, what exactly is z bar t bar? For this, the expression is z bar t bar, whereas this is zt. So my overall expression for C is zt plus z bar t bar. Okay. Similarly, I can proceed with the last one for D. So for D, once again the same don't care terms are same, and for the output D is equal to 1 for 0, and it is 1 for 2, and it is 1 for 4, and 1 for 6, then 1 for 8. Okay. Anything more? Nothing. So what I can do is, I can combine this 4. I can combine with this 4. Totally 8 combinations, 8 minterms combination. Now what is that? That is, there is t bar. So D is t bar. Is it that true? If I make t bar, it becomes t. So from the table also it is clear. Whatever the expression I got it, and what is there in the table, both are same. Now I can recollect the expressions. Expressions for A, expression for B, expression for C, expression for D. From this I can realize the circuit, which is converter, my binary to access 3 converter. So for D is t bar, for C is ZT and Z bar, T bar and ZT. So I remember, for C, Z bar, T bar, ZT. And what is the A part? For A, how much I got? A plus YT plus YZ. A plus, it's not A, X plus x plus yt plus yz. Okay, so your expression for a is x plus yt plus yz, x plus yt plus yz. Now if you look at the expression for b, what expression I got it for b? Y bar z, y bar t, y bar z, y bar t plus y z bar t bar plus y z bar t bar. So now what I can do? It's very simple. To get a, I'll take x, I'll take yt, give it to AND gate. Then you take yz. This is x, this is x, this is y and t. Next is y and z. So y z. So you R them together. If you R them, I'll get a. Okay. Then one is y bar t, one is y bar, another one is t. One is y bar z, y bar and z. Then y z bar t bar, y z bar t bar, and them R them together. So if you R them together, what I am going to get? B. Next you take, is it XOR gate or XNOR gate? So XNOR gate. So take C and D, give it XNOR gate. You will get your, sorry, I need to take Z and T. So you take Z input, T input, then you will get C. So you take an inverter and give it to what exactly I want. I want D. You give the input as T. So X, Y, Z, T are inputs, A, B, C, D are outputs. Now the binary to XS3 code converter is designed.